The electric field is a component of the electromagnetic field. It is a vector field and is generated by electric charges or time-varying magnetic fields, as described by Maxwell's equations. The concept of an electric field was introduced by Michael Faraday. Definition: the electric field at a given point is defined as the force that would be exerted on a stationary test particle of unit charge by electromagnetic forces. A particle of charge would be subject to a force. Its SI units are newtons per coulomb or, equivalently, volts per meter, which in terms of SI base units are kilogram ms-3a-1. Superposition principle. Electric fields satisfy the superposition principle, because Maxwell's equations are linear. As a result, if and the electric fields resulting from distribution of charges and a distribution of charges will create an electric field. For instance, Coulomb's law is linear in charge density as well. This principle is useful to calculate the field created by multiple point charges. If charges are stationary in space in the absence of currents, the superposition principle proves that the resulting field is the sum of fields generated by each particle as described by Coulomb's law. Electrostatic fields. Electrostatic fields are fields which do not change with time, which happens when charges and currents are stationary. In that case, Coulomb's law fully describes the field. Electric potential. By Faraday's law, the electric field has zero curl. One can then define an electric potential, that is, a function such that this is analogous to the gravitational potential. Parallels between electrostatic and gravitational fields. Coulomb's law, which describes the interaction of electric charges, is similar to Newton's law of universal gravitation. This suggests similarities between the electric field E and the gravitational field G, or their associated potentials. Mass is sometimes called gravitational charge because of that similarity. Electrostatic and gravitational forces both are central, conservative and obey an inverse square law. Uniform fields. A uniform field is one in which the electric field is constant at every point. It can be approximated by placing two conducting plates parallel to each other and maintaining a voltage between them. It is only an approximation, because of boundary effects. Assuming infinite planes, the magnitude of the electric field E is, where delta is the potential difference between the plates and E is the distance separating the plates. The negative sign arises as positive charges repel, so a positive charge will experience a force away from the positively charged plate, in the opposite direction to that in which the voltage increases. In micro and nano applications, for instance in relation to semiconductors, a typical magnitude of an electric field is in the order of 70061000000000000000000000000000000000000000000000000000000000000000000000000 Vm-1, achieved by applying a voltage of the order of 1 volt between conductors spaced 1 micrometer apart. Electrodynamic fields. Electrodynamic fields are fields which do change with time, for instance when charges are in motion. The electric field cannot be described independently of the magnetic field in that case. If A is the magnetic vector potential, defined so that one can still define an electric potential such that one can recover Faraday's law of induction by taking the curl of that equation which justifies, a posteriori, the previous form for E, energy in the electric field. If the magnetic field B is non-zero, the total energy per unit volume stored by the electromagnetic field is where epsilon is the permittivity of the medium in which the field exists, its magnetic permeability, and E and B are the electric and magnetic field vectors. As E and B fields are coupled, it would be misleading to split this expression into electric and magnetic contributions. However, in the steady-state case, the fields are no longer coupled. It makes sense in that case to compute the electrostatic energy per unit volume. The total energy U stored in the electric field in a given volume 5 is therefore further extensions definitive equation of vector fields in the presence of matter. It is helpful in electromagnetism to extend the notion of the electric field into 3 vector fields, rather than just one, where P is the electric polarization, the volume density of electric dipole moments, and D is the electric displacement field. Since E and P are defined separately, this equation can be used to define D. The physical interpretation of D is not as clear as E or P, but still serves as a convenient mathematical simplification. Since Maxwell's equations can be simplified in terms of free charges and currents, constitutive relation, the E and D fields are related by the permittivity of the material. For linear, homogeneous, isotropic materials, E and D are proportional and constant throughout the region. There is no position dependence. For inhomogeneous materials, there is a position dependence throughout the material. For anisotropic materials, the E and D fields are not parallel, and so E and D are related by the permittivity tensor, in component form. For nonlinear media, E and D are not proportional. Materials can have varying extents of linearity, homogeneity and isotropy.